Okay, so the next type of circuit that we need to talk about is something called a parallel circuit. And so in parallel circuits, we have more than one path that the charges could follow. So in a series circuit, there's only one path, and each charge has to go through all the resistors. In a parallel circuit, there's at least two, probably even more possible paths that a charge could follow. And so that has an effect on the equivalent resistance and the total current in the circuit and the voltages. So we're going to talk about those. To give you an idea what I'm talking about, I kind of built the circuit in FET, so we're going to try something new here. And I'm going to close the loop here. Okay, so right now we have the charge just going around this one loop and through this resistor. And I have put them some ammeters here to measure the current, and so we see, okay, my total current going through the battery is 0.9 amps, and since I only have one loop, I now have 0.9 amps going through that as well. Now what I'm going to do is I'm going to open up this loop as well, okay, and what this loop is going to do, okay, is going to provide another pathway, and I want you to notice what happens here. First of all, the total current in my whole circuit just increased. Okay, now this battery is providing charge to both this loop and this inner loop right here. Okay, so the total current has gone up. I also want you to note that the total current going into this junction here, this meeting point, is 1.34 amps, and the sum of the current in the two loops is also 1.34 amps, and this is due to conservation of charge. Okay, so we can't lose charge. If we have 1.34 coulombs per second going into this junction, when we look at the current between these two sides, it has to be 1.34. The other thing I want to note is the voltages. Okay, so I have like this little voltmeter here. I'm going to measure voltage across this battery, and it's a 9-volt battery. Okay, now these resistors, if I look at the voltage across this resistor, we're going to see that it's also, it's about 9 volts. Okay, it's also going to be 9 volts. And across this resistor, it's going to be 9 volts. Okay, just to prove to you that it actually does change. If it's between 2 points, it's going to be 0 volts. So, okay, so what's happening here? Right here, we have a 9-volt potential. And over here we have a 0-volt potential. Okay. Now, the difference potential between the two sides is the voltmeter shows, and the voltmeter shows you potential difference. It's going to be 9 volts altogether. So this whole side is going to be at 0 volts. All this conductor stuff is at 0 volts. Okay, and all this side is going to be at 9 volts. Okay, so when we have a parallel circuit like this, we'll have one side, let's put it this way, the voltage drop across each resistor is going to be the same. This is different than what we saw in series circuits where the voltage drop across each resistor would be different. Okay, so I just wanted to give you guys an idea of what a kind of a picture in your mind of a parallel circuit. So let's get into the nitty gritty of this and talk more about kind of the mathematics of it. So we're going to talk about two things. We're going to talk about parallel circuits. We're going to talk about something called Kirchhoff's rules. Parallel circuits. Okay, so parallel circuits, this is the schematic of what I was showing you. So we have our current going through, and at each junction, this current will break up. Okay, so the thing about parallel circuits is that each branch can have a different amount of current going through it. Okay, in a series circuit, the current was the same throughout the whole circuit. In a parallel circuit, the current can be different through each branch if each of these resistors are different. Okay, what I can say, so let's call this the total current. So the total current going through that battery will be equal to the sum of the currents going through each branch. You can go on like this. Okay, the voltage, the drop in voltage across each resistor is the same. No matter what the resistance is, that drop in voltage will be the same. Resistor is the same. Okay, so again, as I was saying, this whole side is 0 volts. This whole side is going to be at 18 volts, and this whole side is going to be at 0 volts. And so the voltage drop across each resistor is going to be the same. It doesn't matter what the resistor is. And then the equivalent resistance for the whole circuit. So remember, equivalent resistance is if I were to replace these three resistors arranged in this way with one single resistor, what resistance would that have to be? And so for the equivalent resistance in a parallel circuit, it turns out that you take the sum of the reciprocals of each, that's supposed to be two, of each resistor in each path, okay, and then take the reciprocal of that, okay. So 1 over R1 plus 1 over R2 plus 1 over R3, add all of that together, take the reciprocal of it, and that's going to be the equivalent resistor of each circuit, which means that every time you add another branch, another resistor to this, you're going to lower the equivalent resistance of the circuit, okay, and the current increases as a result of that. Now, we'll work on this in class, okay, we'll do some problems with parallel circuits in class, but I want to mention the two rules called Kirchhoff's rules. And these are just expressions of conservation of energy and conservation of charge, which we went through before. So when we did series circuits, we saw that the voltage drops across each of the resistors. If we add all those voltage drops together, it's going to be the voltage drop of the battery as a whole. We also saw with parallel circuits, okay, so that for each loop that we went around, the voltage drop through the loop has to be equal to the voltage drop of the battery. This is just an expression of conservation of energy. Okay, so this is called the loop rule. As you go around a loop, the voltage drops across all resistors in a loop has to be the same as the voltage drop across the power source or the battery. The other is what we just saw with parallel circuits. The sum of the currents in all branches of a circuit after a junction is equal to the total current going into the junction. Okay, this is what's called the junction rule. And this is a consequence of conservation of charge. I can't have more charge go in than comes out, and vice versa. So I want you guys to be familiar with these two rules. Sometimes they're explicitly used, but I want you to be familiar with like the terminology. The loop rule is a conservation of energy argument. It's about the voltage, the total voltage drop in the circuit, and the junction rule is a conservation of charge thing, and that is related to the current going into and coming out of a junction. So anyway, parallel circuits, Kirchhoff's rules. If you guys have any questions about this, please let me know, and we will work some problems in class.